Hi, my name is Jennifer, and our research topic was the exploration of parameters for developing a silicone nanocomposite ferroelectret. And my mentor was Dr. Bradley. So we made ferroelectrets using silicone sheets, and these silicone sheets were cured into custom molds. And once these sheets were assembled, an engineered foam would be created. And from this foam, we would analyze the ferroelectric property. So what is a ferroelectret? A ferroelectric is an engineered polymer material that's made from foam that can either expand or contract when an electric field is applied to it. So essentially it is the movement from voltage. And our research questions was, 1, can we control the movement of a ferroelectric by engineering voids or pockets in the silicone? And 2, can an engineered silicone foam be made via this technique? In order to make the silicone, we used Slygard 184. And so the smaller bottle you see in the front is the curing agent, and then the bigger bottle behind it, it's the elastomer base. And we used these two materials mixed by the 3-row machine that you see back there. And so once this was mixed, something that starts off as a liquid would end up becoming an elastic solid. We first tried to use the M2 Epilog Fusion laser cutter. And so you see here we used this Kapton tape, and the Kapton tape is made to endure the high levels of temperature that we apply to it, like here in the laser cutter, and then again in the lab oven when we would cure the silicone. So the molds that you see here, the walls are built out of 3 layers of tape, and then in the middle it's just one single layer of tape. And so this is how it would look from a more clear view. So these sides are the 3 layers of tape that we built, and then the one in the middle are those smaller circles, and that's just 1 layer of tape. So these were the results from the laser cutter tags. One of the advantages of using the laser cutter was how quickly we were able to make so many molds and castings. But one of the disadvantages was that the silicone would come out really thin and almost jelly-like. I don't know if you can see it clearly here, but there it is. It's really thin. It would tear easily. And then another issue that we had was that we weren't able to lift up the mold itself without lifting up the tape. And so we weren't able to find a solution to this. And so we moved on to using aluminum tags. And so these are the aluminum tags that we made. We made these using the CNC machine, the CNC milling machine. And we use the CNC milling machine by generating a G-code that tells the machine where to move. So this is how our G-code looked. You could see on the right, that is how it ended up, and then on the left, that is how the G-code simulation predicted it would look like, which is exactly what we wanted. So it just tells the machine where to move so it knows how to make those precise cuts that we needed. So these are the results from the aluminum molds. And one of the advantages of the aluminum mold was having the castings come out sturdier compared to the delicacy of the laser cutter molds. So the walls were made from pure silicone rather than just the Kapton tape, which provided for an easier removal of them so they wouldn't tear when we would pull them up. And for both of these, to ensure that there was an even layer of silicone in all the molds, we would use an additional aluminum plate on top of it to make sure that everything was evened out. So this is how we made the silicone sheets. We would start off with our mold, which would have a wall, almost like an island, around the single layer tape or the thinner squares. And so this is how it would look from a bird's eye view. You would just see the wall around it inside there. And then we would add in a drop of silicone. And then an additional plate would be added on top in order to make sure that they were all even. And also for both the laser cutter tags and the aluminum, we did have an issue in the beginning where when we would lift up the second tag, the silicone would come back up with it. But adding just a thin layer of Vaseline to the top tag was an easy solution, and it stopped this problem. So then the next step would be to cure the silicone, and we would cure the silicone using the lab oven, and we would leave it in the oven for about 15 minutes at 150 degrees Celsius. And so once they would come out of the oven and we would take them out of their molds, we would get these castings. And so here you see they're individual. You see 1, 2, and 3. So then we would get to our last step, which would be creating our engineered foam. And this would be when we would assemble our sheets together. But in order to assemble our sheets, we use the AC Corona treater. And so what this does, this would give it back its adhesive property after losing it from being in the oven. And so this is a closer look at our engineered foam. You see on the left, that is where we were applying the AC Corona treater. And then once we assembled all of the sheets together, it would look something like on the right. And so that's 3 sheets of the silicone stacked together. And that is what our engineered foam ended up looking like. Following this, we would apply the DC Corona treater. And the DC Corona treater is used to induce polarization to create a ferroelectret. So for our analysis, we use the piezometer, which just measures the voltage in our material, which would give the relationship between the applied voltage and the shape between it. And then we also use the dielectric spectroscopy system as an indirect characterization of the sample. During the analysis portion, using the piezometer, a force of 0.40 newtons was applied to secure the sample during testing. And to find a D33 value, the sample is measured once and then flipped over and measured again. If the material is a ferroelectric, then the value should be positive on one side and negative on the other side. And to find a D33 value, you calculate it by taking the absolute value of the first measure and then adding it to the absolute value of the second measure and dividing it by 2. And we measured a silicone control sample and observed 2.5 on one side and 1.5 on the other. And because both sides gave a positive D33 value, the silicone control sample does not behave as a ferroelectret. Applying the same force to a 2-layer engineered silicone foam, we measured 17.2 on the first side and negative 54 on the second. So this sample produced an overall D33 value of 35.6. We noticed when we polarized a double layer sample with the DC Corona treater for approximately 3 minutes, we got a D33 value of 17 followed by a negative 5 for the opposite side. This gave us a D33 value of 11. And when we charged a double layer silicone on both sides, we ended up getting an overall D33 value of 40. And so after the piezometer, we use the dielectric spectroscopy system, which is a machine that measures the electrical property in plastics, which will tell us how well we're polarizing our engineered foam. And I don't know if you can see there, I circled it. That is the piece of engineered foam. And so you place that on top of it, and it's going to measure the electrical property. These are the results from the dielectric spectroscopy system from the control, which would just be the SliGuard 184. And you can see they're all pretty constant. There's not a lot of changes. And then we get to our results of the ferroelectric, and the same, they're constant, except for the dielectric loss versus the temperature. So in the future, we'll focus on optimization. So we'll compare the data from the dielectric spectroscopy system, the piezometer, and the process parameters. And these can vary from the curing temperature, the AC corona treatment time, and the DC corona treatment time. And the parameters will change in order to optimize our D33 value. And so we'll make samples and see the performance, notice the trends, and then go on from there in order to get the best D33 value. So in conclusion, we were able to investigate the 2 research questions posed for this project, and we were able to create an engineered foam from silicone, and we were also able to confirm via the piezometer that it did act as a ferroelectret. And so I just want to say thank you to Mr. Wheeler for helping me out in the birdhouse and teaching me how to use the laser cutter and all that. And then also to Professor Canaria, who helped me with the CNC machine and the G coding. And of course my mentor, Dr. Bradley, for helping me throughout every step of this research. And Dr. Brim and the Office of Undergraduate for giving me this opportunity.